Okay, today we're going to study inductors and inductance. So I put here inductor and inductance. Inductor. Inductor is just a coil. Okay, a coil like this. This is an inductor. Okay. Now the inductance is L is equal to the number of loops times the flux, the magnetic flux, this I put B here, over the current. So the N is the number of loops. Like here we have 1, 2, 3, 4, 5, 6. So N is equal to 6 here. Now the flux, this is the magnetic flux, is equal to the B field times the area. The reason here cosine theta is 1 is because the area, this area here, vector, is pointing like that, and the magnetic field is also parallel to the vector A. This is the B field. You can see that the area vector and the B field are parallel. So cosine 0 is 1. So we just put BA. So now L is equal to N, I put N, the flux, I put BA, and then over the current. Now, we studied the B field. If you look at the previous videos, the B field for a solenoid, for inductor, is mu0 times N times I. This small n is just the number of loops divided by the length of the solenoid. Here is the length of the solenoid, that's L. Now, we can plug this, we have here, small n is equal, or big N is equal to small n times L. So I can write this L in terms of small n. So I put here NL, because N is NL, and I put here mu0 for B, mu0, Ni, and here I put I. And you can see here I cancels. So I get N squared L mu0. I forgot here A. I have an A here. You see this A? I put B and I have to put A. So I have an A here. So this will give me L over L is equal to N squared mu0 times A. This is the inductance per unit length. Or I can just find it in terms of the number of loops. So I can put here L is equal. Now, you see I have that N there. So I leave that N there, B. I put mu0, small n is equal to, where is it? Small n is N over L. So I put another N over L. Okay. Remember, I have B. This N is this N. B mu0 Ni. I put I here, and then I put the area A. And now, what I have, you see, I have I, but I have this current here, I. So the current I cancels. And then I have N squared mu0 times A over L. And this is my inductance. You can see it depends on the number of loops. Mu0, which is just 4 pi times 10 to minus 7. The area of this area here of the loop, and L is the length of the solenoid. Now what's so interesting about this, the inductance depends on these dimensions. You can see these are dimensions. This is length squared, this is just a number, this is a constant, this is L. How long is the solenoid? If you look at for the capacitance, C is equal to the area times epsilon 0 over the distance d. And these are also dimensions. It depends only on the dimensions and this constant here. And same thing for the inductance. It depends on the dimensions, the length here, and this number, and on the constant. This is for magnetism, and this is for electricity. You know, so this is very interesting. If you look at the resistor or resistance, I put here R is equal to rho. I put L over A. Now, this rho is just constant. It depends on the material, if it's copper or zinc. So this is specific to that material. So this one doesn't change. Of course, it might change with respect to temperature, but in normal temperature, this is just constant. Now, L is the length of the resistor. This is a resistor. Is the length of that wire. A is the cross-section of the wire. So these are just dimensions. Look at here, dimensions. Look at here, these are dimensions. So L, C, R, they depend only on the material they're made of. So they don't depend on the current or the magnetic field or the electric field. It depends only on dimensions. Okay?